You are here today to announce the new discovery, a stunning revelation about Mars, published on Science magazine, made by a team composed of researchers Enrico Flamini, Elena Pettinelli, and Roberto Rosei, belonging to Italian Research Center and the universities. They are here today to present their findings. These are results of a study from the Italian radar marsis on board the ESA Mars Express probe.
And the fact that we have found liquid water in on the subsurface, of Mars. This is a work that has been done by a team that is formed by a lot of people, as you can see, 22 persons actually, and three of in fact, the first evidence that water was largely present in the past on Mars last the times of the Viking mission, so almost 40 years ago, when there was the evidence that lakes and rivers, deltas were present on Mars. Here we see, for example, an example of what is a Madeline Valleys, that is a long river, 600 kilometers in the length, and is actually a long channel that eventually is draining into the crater, the Gusev crater. Well, for this reason, what we see today, that is a picture in which water is mostly present as ice on the surface in a north polar caps and in the south polar cap, is and also is present as permafrost, so mixed with the soil again in an iced form. And the fact that for sure in the past most of the water has been swept out by the solar wind, and provided us the idea that, as in other planets, and in the case of the Earth, for example, some of the water that was once present on Mars should have migrated to the subsurface and eventually remained trapped there, possibly since the time when Mars was wet on the surface. So something that is indeed was this the real question that we had: where the water has gone, where the liquid water has gone, is only in the ice form, is only the one that Mars has lost at a certain point in time, or can be still hidden in the subsurface. And that's the reason why on December 1996, when ESA announced during International Mars Exploration Working Group meeting held in Cocoa Beach, the intention to realize Mars Express, an F mission, a fast mission, a low cost, as he proposed to include on the side of the other instruments that were actually belonging to a former mission that was lost, Mars 96, the Soviet Mars 96 mission, to include also a completely novel instrument, never flown before, and with no previous experience in analyzing other planets.
How a radar works in a simple way. So you have an antenna that sends the electromagnetic waves down. Okay, when the electromagnetic wave impinges on the surface, can be reflected back, like in this, and a part of the energy penetrate down to another interface and got bounced back and got gathered by the antenna. Okay, so if you have a layer structure, like in this case, what you recorded in the antenna, essentially, you measure the two-way travel time, is the time that the impulse takes to arrive to the interface and comes back, and the amplitude of the signal. Okay. So, big question: why is the radar sounder the best method to look for underground water? Okay, we know this since probably the 50s on the Earth, and I show you this because these are the two extreme but best environment for propagation of the electromagnetic waves at radio frequencies, so in the megahertz on the Earth. One is a very dry environment, and another one is a very cold environment. Essentially what we would like to have as a material to investigate at depth, what we would like to have is an electromagnetic wave that impinges on the surface, entering the second medium, and propagate without attenuation, so with the minimum attenuation possible. So we have to search for areas, for example, on Mars, where this technique can be successfully applied. And there are several areas on Mars where we can apply the radar, of course, and that's why it was designed and made. One is some dry areas in some part of Mars, and the other important part are the polar caps. And we know that the polar caps, we knew before marsis start to collect data, that the polar caps are mainly made by water ice with some layers on top of CO2 ice. So this is a great environment to apply the radar, and in particular ice. Ice is a very transparent medium, especially if it's cold and pure to the electromagnetic waves. So how can we detect liquid water below Martian polar ice using the sounder? We use the technique of radar, but how we, in some way, guess that below some part of the South Polar Cap in Planum Australis there was water. And we rely on the fact that some physical properties that we can measure with the radar can tell us if it's a rock, if it's saturated rock, if it's sand, or if it's actually water. In the Martian frequency band, which is between 1.8 and 5 megahertz, you can see from this simple graph of the electric permittivity, this is the real part, but it's enough to understand the concept. You see that the permittivity of the water is very high, is about 80. The permittivity of saturated sediments, so sediments where in the pores or in the fractures there is liquid water, is about 23 or 25. And the dry rock is quite low, on average, let's say 6 or 8. And ice is even lower. So we rely on these differences to see contrast in the electric properties and investigate the subsurface in this way. So if we have, for example, ice on top and rock below this layer of ice, the electric contrast is small, the reflection coefficient is small, and the amplitude is small. You can see here in this simple sketch that the reflection coefficient between the atmosphere, let's call free space, and ice is basically the same as ice and rock. This technique has been extensively applied since the 60s on the Earth, and has been applied especially as I said, in Greenland and Antarctica. You see a drawing of some of the lakes that has been found in Antarctica. You see how complex is the hydraulic system below the ice. And some of these lakes have been detected with the same technique, using a little higher frequency, but the concept is essentially the same. So what we would like to see, and what we use to detect and guess, let's say, we say calculate, what was the dielectric constant of the reflection, is explained in this sketch. So you have the radar that sends pulses, and pulses bounce back from the surface, penetrate into the ice, and got reflected by the rock or the bottom material below the ice. And you can see here this is summarized what I was showing before with about the dielectric contrast, that here the amplitude is small, here increase a little bit, here is very large. Okay. Now, what we really have with marsis. This is what you have with data, and you will see that this is just an oversimplification, but we don't know anything. We record these traces, as I said, two-way travel time and amplitude, and we have these traces so we can align due to the position of the orbiter. So what we can say? We can say a few things. Definitely, here there is the surface. So we can know, we can measure quite well from the altitude of the spacecraft. And we see now something different in different areas below the surface. We see this amplitude is low, this is medium, this is very high, okay? So we know that these amplitudes indicate a contrast in the electric properties between the materials above, the material above and the material below, also in different locations. Okay, so we can say probably here there is an interface, a subsurface interface. Now, let's look a little bit more in detail, and this introduce the part that Roberto will tell you about the analyzing and results of the data. So we know from other measurements that this is water ice. We knew from before, and there are other experiments or measurements that confirm this during the years and the missions. We should say that this is very simple. And you will see in the presentation, Roberto, that the traces are much more complicated than this. And what we have to do, we have to analyze these pulses, the feature of these reflected pulses, and extract, trying to find a way to process the data, make modelings, invert the data, to say what is the dielectric property here, here, and here. And this is what we have done with the analysis of the data.
So the reason for the strong echoes was that a lot of energy was able to penetrate into the ice, propagate to the bottom, and produce a comparatively stronger echo simply because the pulse impinging on the bottom of the ice had a higher energy. And so this essentially concluded the first phase of the search for water on Mars. But not everybody was content with this explanation, and the search continued outside the residual cap. And thanks to the effort of our colleagues, several locations outside the residual polar cap were mapped in which the strong reflections could be observed. The problem was these areas were very scattered and of a very small extension. Sometimes they seem to be of the size comparable to the footprint of the radar. And most important, the measurements over the same area in different orbits could yield different results. The good news was then that we were able to map these bright reflections. However, we could do it over a very limited area because this raw data collection mode limited strongly our capability to observe. We had only short stretches of data collection. And now we found this particular place that was already suspected to harbor, let's say, to have bright reflectors in it, which is mapped over a mosaic of the south pole of Mars. So the gray square encompasses a false color map of basal reflectivity produced using the 27 observations we have available and shows in false colors the brightness of the reflection from the bottom. And of course, the blue area, well, is the one that has the strongest reflections.
Thank you for this connection. I'm at this moment in Kourou, where we just launched an Ariane 5 with 4 Galileo satellites on board from the European spaceport here in French Guiana. The launch has been really great, so I'm really pleased to have this opportunity to shortly comment with you this extraordinary discovery of the water on Mars. I think what has been done with the observation which has been just published is really amazing. We knew that Mars, about 3 billion years ago, was full of water, and something has happened in between, and most of the atmosphere and the water with it has gone. But we know about the ice, and with this observation by marsis, we have evidence that below the ice, deep below the surface of Mars, there are lakes and great quantity of water. This clearly is exciting because we know that water is almost everywhere in space. And we have a proof on our planet that where water is abundant, life can prosper. So we are really excited by the fact that there is still a large amount of water on Mars, because we are working on this ambitious mission with ESA, ExoMars 2020, to drill the surface of Mars a couple of meters down, and hoping that we can tap some of the ice or the water to analyze it. And because clearly the opportunity to study water underground give us the hope we can find something interesting, something important about possible life on the red planet. If the water is everywhere in the universe, and if the life is very much connected to water, then we can hope that life is also almost everywhere in the universe. And the closest place we can check is exactly the red planet.
La domanda che viene subito, the first question is about the life. This discovery permit us to think about what kind of form of life. I ask to
what with this instrument we may say is there is water. The water is screened by the solar, the cosmic radiation and solar radiation, is liquid and is salty and is in contact with rocks. There are all the ingredients for thinking that life can be there or can be maintained there if life once existed on Mars, a Martian surface. However, marsis cannot say anything more, so we may guess about what are the conditions there and if the conditions are favorable or not, but is not this instrument that can directly answer the question if life is there.
Just a curiosity, how big is the minimum size of the region in kilometers? Or?
The patch, the blue patch on the figure that was shown before, is about 20 kilometers across. The thickness of the lake is difficult to determine because the radar is not able to penetrate below the surface of water. But as a minimum, it has to be of the order of 1 meter. This is because otherwise the radar would just see through the water, not see that. Which amounts to, by some back-of-the-envelope computation, still to several hundred million cubic meters of liquid water.
Roberto, maybe I missed in your presentation, how deep is below the surface this body of water that you have detected?
I'm afraid I didn't say it. I was too excited. And the answer is 1.5 kilometers.